Hey guys, it's Dr. D-Flo, and in today's video, we're gonna build and test what I believe is the most capable desktop CNC mill on the market, the DMC2 Mini. As its name suggests, this mill sits on a standard 24-inch workbench and plugs into a residential outlet. Even with its small form factor, its machining envelope is 12 inches by 7 inches by 5.5 inches. There is 6.25 inches of clearance between the spindle and bed, which is about 50% more than other machines in its category, allowing for larger tools, thicker stock material, and more work holding options. But what I'm most impressed with is the linear motion setup. Ball screws and linear rails are used for all three axes. The 3 horsepower, 24,000 RPM spindle moves in the X and Z, and the table moves back and forth in the Y. The max travel speed is 10,000 millimeters or 400 inches per minute. While this is a stepper motor system, the motors have encoders to detect crashes. There are also some other features that you would expect on a full-fledged vertical machining center, but not on a desktop mill, including a one-shot oiler to keep everything running smoothly, a coolant pump which can blast away chips, and automatic probing for locating stock material. And it only costs $2,500 at the time of making this video. Of course, there is a catch. You're purchasing a kit that comes in quite a few pieces. How hard was it to put together? I will show you later in the video, but if you can complete the build, then you will have an impressive piece of machinery. But why was I interested in the DMC2 Mini if I have my larger mill? Well, I'm looking for a machine that I can train my students on, but it needs to be small so I can fit multiple on a rack, and of course, cheap enough that I don't go bankrupt every time a student crashes one. Bonus points if I can source broken components myself. More machines equal more opportunities for students to get hands-on time and learn how different CNC machining is from 3D printing. Of course, if this turns out to be a good teaching tool, it would also be a great learning tool for you to have at home. However, the idea of having a benchtop CNC machine is a bit of an oxymoron. Subtractive machines need to be large to be able to remove deep cuts of material without chatter. This requires a heavy and rigid frame. Now this can sometimes be circumvented by using a high RPM spindle to take small but quick bites out of the material. This works particularly well for aluminum, but is not so great for harder materials like steel or titanium. While you may not need a steel casting that weighs hundreds or even thousands of pounds for a benchtop mill, rigidity is still important. And one of my favorite features of the Mini is that it is constructed from steel, and you can definitely tell. It weighs in at about 110 pounds. I have plenty of test cuts to show you out of ferrous and non-ferrous materials. I do have some experience with benchtop mills, so I know what I'm looking for. Through my school, I first purchased a Bantam Tools mill for $3,800 about 3 years ago. I was drawn to its enclosed form factor, conductive probing, and user-friendly CAM software. But I had quite a bit of issues with it, eventually requiring a new motherboard, and I kid you not, they doubled the price and started to lock software features behind a pro license. Those were all deal breakers for me. I saw the DMC2 Mini being showcased by Omar, the CEO, on YouTube, so I reached out to see if he would send one out for me to review. I thought this would be a great way for me to trial the mill while at the same time giving you a look at it. I do want to emphasize that I am not being paid to make this video, but I did receive the kit in return for making an honest review. Sheriff will have no input on the final video. Let's get to the assembly, but stay tuned till the end as I will put this mill through its paces. My wife graciously allowed me to assemble the mill in the kitchen since I don't have enough space in the garage. As you can see, the sheer number of components in this kit is a bit daunting. The instruction manual is 200 pages long. For about $2,000 more, you can buy an assembled version, which is a good option if you're new to machining or haven't built a 3D printer or CNC router before. But if you're on a tight budget or want to understand this machine intimately in case of repairs, then follow me down this DIY path. According to the website, this assembly could take 20 hours or more. To keep this video reasonable, it won't be a detailed guide for every component and fastener. Most of it will be sped up. However, I'll slow down to highlight features that I like and those that raise questions. Let me get just the components that I need for the base in front of me, and then we'll get started. For the mechanical assembly, only hand tools are needed. Wrenches, hex keys, and a digital protractor are about it. I want to again highlight that the frame is heavy tube and plate steel. It may be possible after assembly to fill the channels with epoxy granite for even more rigidity. So far, the assembly has been smooth. The plates and tubes are fiber laser cut, which means there's a slight angularity to the holes. This requires a bit of effort to align all the bolts properly, but I haven't encountered any binding issues. Speaking of bolts, the instructions call for a surprisingly large number of them. I've installed 160 M5 bolts of various lengths so far. The upside is that once everything's assembled, it's incredibly solid and won't easily come apart. With most low-cost CNC machines, whether it's a 3D printer or a router, you typically tram the frame by keeping all the joints loose, then checking each corner to ensure everything is perpendicular. You tighten the bolts, check for squareness again, and repeat until satisfied. Doing this with 160 bolts would be a nightmare, but fortunately, what I really like about this mill's design is the inclusion of built-in tramming points, which eliminates the need to loosen every single bolt. Here's an example of one of those tramming points where the X-axis will attach. It's a bit hard to see, but there are 2 threaded holes, one on each of the vertical members. 2 M5 bolts threaded through these holes from the back will press against the X-axis, pushing it outwards. This will allow us to set the tilt of the X-axis and ultimately the spindle. We want the spindle to be perpendicular with the table. Let's go ahead and get the X-axis installed and tighten everything up. I will get back with you shortly to talk about the linear rails and ball screws. One of the reasons I'm excited about this mill is its use of ball screws and linear rails. This setup is a major step up compared to the rods and lead screws you typically find on benchtop CNC machines. Let's break down why this is such a big improvement. First, the 12mm ball screws with a 4mm pitch are significantly more efficient than lead screws. Lead screws rely on sliding friction, which means they lose energy to heat and wear. Over time, the brass nut on the lead screw wears down, causing motion inaccuracies. With a benchtop mill, we want the high RPM spindle to take quick, small bites, so travel speed is critical. A cut that a larger mill could make in a single pass will likely require multiple passes on a benchtop machine, meaning the linear motion components will see more mileage. Fortunately, this mill includes fittings and tubes for a one-shot oiler, which will keep the ball screws running smoothly and reliably for a long time. Next, let's talk about the linear rails. These are HGR 15 rails, meaning they are 15mm wide and 15mm tall. Unlike linear rods, which can flex under load, linear rails are hardened steel tracks supported by the frame along their entire length. The mill uses 2 carriages per rail and 2 rails per axis. That gives us 4 carriages per direction, distributing the load over a larger area and reducing the chance of deflection. The result is better rigidity, smoother motion, and more accurate cuts. Plus, linear rails also have their own fittings for oil lubrication, further ensuring smooth operation. Let's go ahead and get the ball screws and rails installed on the mill. Preparing the ball screws took a bit longer than expected. You can see that the Y-axis ball screw, which sits beneath the table and is exposed to the most chips, has an accordion cover for protection. I really like this feature. It's another example of how the designers were focused on durability. But one design choice I didn't like is the double nut approach used to eliminate backlash in the X and Y axes. All nuts have some inherent backlash, or unwanted motion, between the threads, or in this case, the ball bearings and the tracks they ride along. To reduce this, you can use two nuts and tension them against each other. The idea is to eliminate the play, but the amount of tension is critical. Too much and you get excessive wear, too little and you don't fully eliminate the backlash. Typically you can buy a double nut ball screw with a factory set preload, but in this build the instructions call for two standard ball nuts bolted together with some lock washers acting as springs between them. You then have to guess how much to compress the washers. My concern is that once everything is assembled, it'll be difficult to fine-tune that preload. Next, we'll start to mount the motors, add the linear rail carriages, and run the lubrication lines. As you can see, I've got the Y-axis and the X-axis complete. We're now going to work on the Z-axis, which is going to hold the spindle, and that's going to move the cutting tool up and down. I installed the Z-axis and used a machinist square to ensure it was perfectly vertical in both directions. The mounting plate holes provided enough clearance to swivel the Z-axis and get it aligned from left to right. For the front to back alignment, I used the tilt trimming point that I showed earlier. So far, it's been surprisingly easy to get everything square. That said, not everything has been smooth sailing. While I've been impressed with the foresight to include a lubrication system, its implementation has been, let's just say, a bit tight. On the x-axis, you have to route the lubrication lines between the z-axis mounting plates and the rail. I was trying to position the lines so that they wouldn't rub against the rail or kink as the X-carriage moves. Unfortunately, I fiddled with one of the lines a bit too much, and the oil fitting snapped off the carriage. Definitely more my fault than the kit's design. Fortunately, there's another oil port on the opposite side of the carriage. Unfortunately, I'm going to have to take off the z-axis and flip the x-axis linear carriage around. When working on something this complex, it's almost inevitable that you'll have to backtrack at some point. The key is to set your expectations realistically and hope you catch any mistakes early. I'll make that fix and finish routing the lubrication lines. I'm about halfway through the mechanical assembly, and next up is the enclosure. In those last clips, you saw my wife and I assemble and install the basin. Part of that process involved applying a lot of silicone sealant around all the seams and fasteners. Let's talk about why that's necessary. Most benchtop milling machines don't come standard with any kind of coolant system for washing away chips or removing heat from the cutting tool. Coolant helps cutting tools last longer and results in cleaner finishes on your parts. For these reasons, I consider it an essential feature. You can purchase an aftermarket mist coolant system, which sputters a small amount of coolant directly onto the cutter. The advantage of a mist system is that you don't need to recapture the coolant since most of it evaporates. However, it does have drawbacks. It consumes a lot of compressed air to atomize the coolant, and it's the air pressure that blasts away the chips. When I run my mist system on the mill in my garage, my 2 horsepower compressor runs almost constantly to keep up. An alternative to mist coolant is flood coolant. As the name suggests, flood coolant involves pumping large volumes of coolant over the part. This method is much more efficient at removing chips and cooling the workpiece. However, it requires a way to recirculate the coolant. Any gaps in the enclosure can result in a huge mess. Additionally, you have to filter the coolant to remove chips and contaminants before it cycles back through the pump. Flood coolant is generally more complex to implement, so it's typically only found on full-fledged milling centers. That's why I was surprised to learn that the DMC2 Mini comes standard with a flood coolant system capable of 40 psi. Of course, implementing flood coolant at this scale could go one of 2 ways. It could be very effective at evacuating chips, or it could turn into a complete mess. Actually, those 2 scenarios aren't mutually exclusive. The amount the enclosure leaks depends entirely on how well you seal the seams and fasteners in the basin. Fingers crossed we didn't miss a spot. Here's the pump that comes with the kit. It's rated for 7 liters or 2 gallons per minute. You can adjust the coolant flow rate using this potentiometer, and the green button toggles the coolant on and off. Before we move on to the top and back of the enclosure, let's talk about the work offset probe. While I had my soldering supplies out, the instructions walked me through modifying this manual probe. It lights up when the ball bearing contacts the surface, but the modification allows it to send a digital signal to the mill when it touches off a surface. This involved removing the batteries and soldering a wire to the probe's PCB. I will admit, I am a little concerned about the accuracy of this probe. It feels a bit cheap, but if it's repeatable to within a 1/1000th of an inch, I'll be satisfied. As I mentioned earlier, I'm planning to use this mill as a training tool, and probes tend to get sacrificed in this kind of environment. So if it works and it's affordable, I'm all for it. So I caught another mistake on my part. This plate is upside down. This hole right here should be on the bottom, which would allow for the back panel to bolt to it. I'm not sure how it took me so long to figure this out. The machine is literally not symmetric with this plate sticking up in this orientation. I'm going to flip it around really quickly. Next, I've installed the stepper motors for each axis. These are NEMA 23 motors with 2 Newton meters or 280 ounce-inches of torque. Desktop mills are often seen as ideal for cutting small parts, like those for watchmaking. While you can improve a stepper motor's accuracy by dividing its rotation into smaller steps, this reduces its holding torque. In simple terms, you need a motor with high torque to make precise movements while resisting cutting forces. That's why it's disappointing to see some desktop mills use NEMA 17 motors, which typically have about 1/3 of the torque of these NEMA 23 motors. The motors are equipped with encoders to track the position of their shafts. If you command too heavy of a cut or the machine crashes, the encoder detects that the motor isn't rotating as expected and pauses the program. This feature provides peace of mind, especially when running the mill unattended or with students. It's time to prepare the 24,000 RPM 2.2 kilowatt spindle for mounting. I much prefer spindles with these square form factors as they bolt right to the Z-axis. Round spindles can turn in or slide out of their mounts. Next to the spindle, there's a magnetic holder for the work offset probe. I'm used to running probes that fit directly into the spindle collet, so this setup is a bit different. With the probe mounted off-center, there will be an X and Y offset relative to the spindle center. This offset will need to be carefully calibrated to ensure accurate probing. I would like to point out that this probe will not work for plastics because it's triggered when it senses a conductive path back to the frame. This could also impact work holding as the popular painter's tape method insulates the workpiece from the table. When I ran my old X-Carve CNC router, which was belt driven, I would have to be so careful when changing the end mills because the force that I applied when tightening the collet could unintentionally move the cutting head. This would require a reprobe. That's not going to be a problem here with the ball screws and beefy stepper motors. On the side of the machine, I've attached the one-shot oiler and manifold. Lubrication lines will be terminated at the manifold during the electrical wiring portion, as some of these tubes will be managed with the wires. Finally, it's time for the front cover. It's not called the top because the Z-axis extends too far up, so a small portion of the top is left open. I'm grateful for the cover, but it would have been nice if it was hinged so that you don't have to leave a spot open next to the mill to set it down. Also, when the 24,000 RPM spindle ramps up, I'm going to want a thicker piece of acrylic in case a part is thrown. Throughout the assembly, I've been wondering how it was possible to sell a kit with this many high quality and custom components for this low of a price point. I've finally found where some of the corners were cut to keep costs down: the electronics. I'm about to be critical, but to preface, this is exactly where I want the cheap components to be because it's much easier to upgrade the controller board than, say, the rigidity of the X-axis. This may be the nudge that you need to upgrade to your desired interface, but for the purpose of this video, I will stick with the supplied Mach 3 USB board clone. This controller needs to be driven by a PC running Mach 3, which will set you back $175 for a license. Not ideal since Mach 3 is deprecated. The controller board stacks on top of a custom breakout board for making wiring a little bit easier, which is much appreciated. Those boards, as well as the stepper drivers, are enclosed in this box, which will be attached to the back of the mill. With With a moving table design, the X and Y motors and limit switches remain stationary. This means the Z-axis wires are the only ones you need to worry about having enough slack without getting pinched during the movement. The instructions recommend an umbilical cord setup, or at least that's what it's called in the 3D printing world, where all the wires are bundled together and hang off the back. I did my best to gather all the wires into the provided sleeving, but the DB15 encoder connector was a bit too large to fit in. I then attached the enclosure to the back of the machine and terminated the limit and stepper motor wires there. Once that was finished, I routed all the lubrication lines to the manifold. Finally, the controller board, stepper drivers, and spindle need power. I'll start by wiring up the variable frequency drive, or VFD, which will power the spindle. The VFD takes a 110 or 220 volt connection from the wall and a low voltage signal from the microcontroller, which will set the spindle speed. The regulated power supply is for the stepper drivers. The kit should come with a 36 volt supply, but mine accidentally shipped with a 60 volt. I'm not complaining because a higher voltage allows for improved high-speed performance of the stepper motors as the current can get in and out of the windings faster. Sheriff did offer a 36 volt replacement, but I declined. The only modification that I needed to make for this higher voltage was to wire the power supply directly to the stepper drivers and not through the breakout board. To power the controller board, a 12 volt power adapter was provided. Actually, two of them. The first is for the controller board and the second is for the coolant pump. According to the instructions, the pump can cause voltage spikes when it starts up, which can disrupt the controller board's operation. Two of them keeps that power separate. I don't know if you're keeping track, but we're going to need an entire power strip to plug in this mill. There are 4 AC plugs, and the other kicker is that there is nowhere in the electrical instructions to mount the VFD and power supply. Look, the power supply fits perfectly here. I can imagine this top enclosure extending all the way down the back of the mill to hold these components. I believe that a proper enclosure would be worth the extra cost to both increase safety and decrease the overall footprint of the mill. I'm going to quickly 3D print a backplate to hold these components. I will also make changes to the power distribution so that the mill only needs one AC outlet. Specifically, I'm going to switch to one 12 volt power supply and then use a 12 volt to 12 volt regulator to make sure that the controller board is not affected by the voltage spikes given off by the coolant pump. I know that I could have sorted this out with a flyback diode and a capacitor, but I had this regulator sitting around. I'm also going to use some terminals for distributing the AC mains to the 12 volt and 60 volt power supplies, as well as the VFD. I will put the CAD file and parts needed to make this upgrade on my website. While I'm waiting for the new enclosure to print, I connected the coolant pump. This is not a submersible pump, so it will need to be on the outside of the reservoir. It will pull coolant through this filter to keep chips out. A larger tube slides over the coolant return ramp to funnel the coolant back to the reservoir. My new enclosure is tight with all the different components in it, but I have a cutout for the exhaust of the VFD and 2 intake fans in the bottom. I'm hoping that this active cooling is enough to keep the temperature down. In my opinion, this solution is safer than having the power supply and VFD beside or underneath the mill, especially considering the flood coolant. AC power comes through one plug and is distributed to the 60 volt power supply, 12 volt supply, and the VFD. After mounting the enclosure, I was able to trim down the spindle, power, and signal wires for better wire management. I covered the exhaust hole for the VFD with a filter to keep the chips out. The front of the enclosure is louvered to allow hot air to escape, but has an overhang to keep coolant and chips out. I relocated the VFD screen to outside so that it's easier to check for errors. And finally, we're ready to turn it on. First up, we'll home it. Nice, it looks like all the axes are moving in the correct direction. and all the limit switches are working. I did notice that the X-axis motor and its mount, as well as the Z-axis motor and its mount, rock back and forth as they were moving. That's a bit odd. I may need to address that later, but let's go ahead and check and see if the hand wheel works. Nice. How about the spindle? Here is 10,000 RPM. Here is 24,000 RPM. That is a lot of power for this baby mill, but hey, we're here for a benchtop mill that can actually chew through material. Let's check the backlash of the X and Y axes. Starting with the Y, I'll move the table towards my indicator. I will zero the indicator and move it 1 millimeter away to see if there's any reversal error. Wow, that's impressive. Only about 7 microns or 2 10,000ths of an inch off from 1 millimeter. Let's check the X now. Only 3 microns or 2/10. Fantastic. I was pretty skeptical about the DIY double ball nut, but that seems to work well. Before we take our first cut, I need to recheck the tram of the mill. One thing that I was worried about with the push-pull adjustment of the X-axis was if once I got pushed too far forward, then the X-axis would be at a diagonal to the Y. I used an indicator to sweep on the back of the Y-axis table to check if the X-axis and end of the Y-axis were parallel. Over 200 millimeters, I'm seeing about 30 microns or 1 thou of variability. That's within spec for the mill. Let's see it move at its full 9,000 millimeters per minute feed rate. Wow. The last step in the tramming process is to machine the surface of the bed. Through this, we are creating a reference surface that is perfectly aligned to the X-axis, ensuring the future workpieces sit flat relative to the tool's path. With the tram complete, it's now time to prepare the bed for work holding. You can machine in T-slots for conventional work holding or drill a grid of M6 holes for modular vices. The aluminum bed is removable, so you could create a mini pallet system with different work holding for different jobs. Just make sure you install the beds in the same orientation each time. I'm going to stick with the provided work holding and install this vise. A vise like this would be too tall for most benchtop machines, but the extra Z clearance on the DMC2 Mini will let you cut stock material that sticks 76 millimeters or 3 inches above the vise. The machine is currently drilling holes for both dowels that will align the vise and threaded holes that will secure it down. With the vise installed, let's set up the touch plate and the XY work probe. Sheriff has an excellent video on calibrating both, but I do want to briefly talk about how the XY offset is calibrated for the work probe. You start by using a dowel of known diameter and a multimeter to determine the machine coordinate where the dowel just touches a 1, 2, 3 block. When continuity is achieved, the center of the spindle is exactly 1 dowel radius away from the block. Next, you repeat the process using the probe, touching off at the same position. The offset value is then calculated as the difference between the machine coordinate where the probe triggers and the coordinate where continuity was achieved with the dowel, plus the radius of the dowel. This process is done separately for both the X and Y axes. You can perform it multiple times to check the probe's repeatability. I'm seeing about 25 microns or 1 thou of variability. Honestly, this is much better than I expected and very respectable for what is likely a $10 probe. The oil lubrication system is pretty standard, but I wanted to highlight the manifold, which distributes oil to all the components. It's equipped with spring-loaded control valves. Here's how it works. You pump the system once, and these silver buttons pop out. Pressing a button sends a precise shot of oil down the line it controls. This ensures that oil only flows where it's needed, which is ideal because without this system, some lines might receive more oil than others due to gravity. Let's go ahead and mix up the coolant so that we can check for leaks. I'm going to use Fusion Cool 2240 at 10% concentration in distilled water. We can turn the pump on. Let's go ahead and increase the speed. I'm not sure if we should have this high of a flow rate with there being no real top to the enclosure, but we should get some great chip evacuation. It does look like we have a small pinhole in the front bottom that is dripping coolant, but that can be fixed with more silicone. Let's flip it around to see if there are any problems in the back. So there are 2 more small leaks. One is where the sides come together for the ramp, and there's a small hole directly above that in the basin. Again, easy fixes. What is more problematic is that the return tube can easily kink, causing the coolant to back up. You leave this alone for 1 minute and you will have coolant everywhere. I'm going to purchase a reinforced tube so that doesn't become a problem. I'm also going to place blocks under the mill so that I can use a larger pan with higher sides. I might even include a water detector to cut off the pump if coolant is found in the tray. Now I'm going to get in trouble for spraying coolant all over the kitchen, so let's meet back up when I have the mill in the garage. I'm finally ready to cut my first part, but how long did it take to get to this point? From unboxing to assembly to calibration, I spent about 50 hours over the course of a week. Let me emphasize, this kit is a significant undertaking. I had a lot of fun building it, even with a few mistakes along the way. That said, it wouldn't have been nearly as enjoyable if I made a more serious error that required backtracking on my progress, or if I had tried to chip away at it with just an hour or 2 a day. In that case, this project could have easily have dragged on a month or more. If you decide to tackle this kit, I highly recommend clearing your schedule, maybe even calling in sick for a couple of days, to dedicate focused time to the build. Trust me, it'll make the process much easier. For my first part, I've designed a calibration piece that will showcase various milling operations, including facing, slotting, 2D and 3D contouring, threading, and chamfering. At the end, we'll take some measurements to check its accuracy. I'm not running coolant for this demonstration, so you can see the cutting action more clearly. I'm taking a 1mm depth of cut at 2,000 millimeters per minute with a 6mm diameter tool spinning at 24,000 RPM. I'm running at about 75% the feed per tooth Sheriff publishes, leaving a little speed on the table. Next, I'll cut the outside perimeter of the part using a 6mm diameter end mill with longer flutes to accommodate a 15mm depth of cut and a 0.6mm step over, which can induce chatter if the tool doesn't decelerate quick enough. To mitigate this, I'm using a more conservative feed rate of 1500 millimeters per minute. Even so, look at those chips fly. After contouring, the 6mm tool will quickly rough out some material with an adaptive toolpath. Then, a 4mm ball end mill will finish the top of a hemisphere geometry with a scallop toolpath. Next, I need to create 4.2mm holes to prepare for thread milling 2 M5 threads. One of the main drawbacks of a high-speed spindle like this is its lack of torque for drilling. Instead of drilling, holes are created by spiraling down with an end mill smaller than the hole's diameter. This works well, but is slower than drilling and limited by the shorter flute lengths of the end mill, making deep holes challenging. Low torque also affects thread cutting. If you've ever tapped a hole by hand, you know even small threads require significant force. To address this, I'm using a thread mill, a tool with a triangular profile. By helically moving the tool upward, it creates the desired thread form. For demonstration, I've placed one hole on the edge of the model so you can clearly see the thread mill's profile as it cuts. Since thread mills can't handle a heavy chip load, this process often requires multiple passes. This M5 bolt threads in nicely. To showcase this mill's ability to handle fine details, I'm using a 1mm end mill to engrave my logo. Finally, I'll chamfer the top edges of the part. To remove the excess material from the back, I'll flip the part over and use a 10mm insert mill. While that's underway, let me know if this walkthrough of making the calibration part piqued your interest in a more in-depth video guide. High-speed machining has some subtle but important differences from traditional machining. I'd be happy to dive deeper into these nuances in a future video as I continue to explore what this mill can do. The machining time for the top half was 8 minutes and 46 seconds. The backside facing added another 5 minutes and 41 seconds since there was quite a bit of material to remove. That brings the total machining time to 14 minutes and 27 seconds. I'm impressed by how well this small mill can chew through material, and this speed didn't come at the expense of quality. The surface finish is excellent. There are some marks from where I gripped the part in the vise for the second operation, but looking at this first op piece, the finish is smooth and clean. Now I wish I could say that this was my first attempt. Unfortunately, I pushed the mill a little too hard on my initial test. When I heard the cutter bogging down on a particularly ambitious slotting operation, I went to hit the emergency stop button. To my surprise, nothing happened. The mill kept moving. I had to weave through my camera tripod legs to get to my laptop, but before I could stop it, the spindle stalled and the end mill snapped. Even more concerning, when the VFD entered an air state, the mill kept running, which means there's no direct communication between the VFD and the controller beyond setting the spindle speed. For small CNC routers, a digital emergency stop button might be fine, but a machine this fast with a 3 horsepower spindle needs a hardwired e-stop switch that cuts power to the entire system. No waiting until the end of a move. As I said earlier, if you buy this mill, assume it doesn't come with a control board, and now assume it doesn't come with a functional emergency stop either. I'll be upgrading to this Maso G3 Touch all-in-one controller, which will replace both the Mach 3 board and my laptop. Yes, this unit is almost as large as the mill itself, but the large screen makes it easier to catch errors in toolpaths and prevents me from fat fingering the wrong button. I'm also considering upgrading to a spindle that's automatic tool change ready, since right now the slowest part of the machining process is swapping tools and reprobing the tool length before each cut. Subscribe if you want to see those upgrades and more. Let's check the accuracy of the part. This measurement should be 20 millimeters, but it's 65 microns or 3 thou oversized. This perpendicular dimension should be 50 millimeters, but it's 156 microns or 6 thou oversized. Typically when a part comes out larger than expected, it's due to tool deflection, backlash in the motion system, frame rigidity issues, or spindle runout. Most of the time, it's a combination of these factors. To diagnose this, I placed an indicator on the spindle nose and pulled on it. I measured 24 microns of movement in one direction and 31 microns in the other, or 55 microns, 2 thou of total play. Then I moved the indicator to the x-axis carriage and repeated the test. This time I saw 6 microns to the left and 22 microns to the right, for a total of 28 microns, or 1 thou of play. This tells me that about half of the total movement is coming from the ball screw backlash, while the rest is from play between the z-axis and spindle. I increased the preload on the x-axis ball screw and tightened all the bolts, then rechecked the play at the spindle nose. Now I'm measuring 12 microns in one direction and 25 microns in the other, for a total of 37 microns of play, which is 18 microns less than before. We're approaching the practical accuracy limits of this mill. I saw similar results when tightening the y-axis ball screw and table. When dealing with deflection issues, increasing the number of finishing passes, or taking lighter cuts as you approach the final dimension can help achieve more accurate results. After making these adjustments and adding 4 more finishing passes, my final measurements are 2 microns, 1/10 of a thou oversized here, and 7 microns, 3/10 of a thou oversized there. Much more respectable. Next, I'm machining taller feet to allow for more vertical drop in the coolant return path. Hopefully this will help with some of the leaks. An extended reach carbide tool like this would likely snap in other benchtop CNC machines due to chatter, but this mill handles it well. Scallop tool paths on this mill are great. They have a low chip load and take advantage of the mill's fast travel speeds. I installed the new feet, and now you can see the new routing for the coolant tube. I used right angle fittings to prevent kinking. While this has helped, it hasn't completely eliminated leaks. If the coolant flow is set higher than 25%, the chip tray overflows. Also during heavy cutting operations, the drainage holes clog with chips. I need to think through a better solution for this. The leaks aren't bad enough to justify ditching the coolant altogether, but I do need to stay nearby so I can shut it off as soon as the operation is complete. When I was diagnosing the deflection issue, something was still bugging me. The X-axis motor plate rocked more than I liked. So I decided to machine a new, thicker right angle bracket out of 2 pieces of aluminum. Check it out. For the final part, I'm cutting a Module 2 spur gear out of 303 stainless steel. Sure, you might be able to cut aluminum on a wood router, but stainless steel is a whole different challenge for benchtop machines. I'll put my cutting parameters on screen, but this is foreign territory for me. Normally on my larger mill, I run lower spindle speeds when cutting stainless to prevent heat buildup and work hardening at the cutting surface. Now I know most viewers love the sound of cutting, but a 6mm end mill cutting stainless on this machine is not exactly pleasant. Take a listen. For that reason, I'll play some music over the top and speed up the machining process just to show that yes, this mill can cut stainless steel. It may have taken a little bit longer than expected, but the surface finish on this stainless steel part is great. To wrap this up, I really like this mill. Online, you often see an impossible wish list for a hobbyist mill. Something compact enough to sit on a bench, yet rigid and fast enough to handle a high RPM spindle and actually cut metal. Oh, and it also has to be affordable. I would have thought that this combination was impossible, but the DMC2 Mini delivers, if you can build it. The assembly is no small task, and some design elements are a bit rough around the edges. The electronics have their quirks, and the motor mounting plates could use improvement. But if you're knowledgeable enough to assemble this mill, you'll have no trouble addressing these issues. Let me know if you'd like to see more content on this mill, and if you made it this far in the video, hit that like button. And with that, I'll catch you in the next one.